In this module we will talk about temperature and heat. Thermometers are devices that allow us to determine the changes in temperature. Shown here are some devices used to measure changes in temperature. We are familiar with the electronic base, which uses integrated devices that are programmed to determine the temperature of a surface. We have a liquid-based temperature device here. Using alcohol or mercury, we are able to determine the changes in the temperature due to the sensitivity of these liquids to heat. We also have a pressure-based device that monitors changes of heat. In this section, we explore what principles govern the changes of temperature and its relation to heat. There have been several types of scale system which have become obsolete or less popular. Currently, Fahrenheit, Celsius, and Kelvin scales are the scales that are globally being used. The scales are developed separately, thus they have different values but can be converted to one for the other. Here we have the conversion of the temperature scales. 0 Kelvin is equal to -273 degrees Celsius or equal to -459.67 degree Fahrenheit. When we say 0 Kelvin, it usually means it is the absolute zero temperature where it is assumed that the particles are not moving. Here we have equations 0,1 and 0,2 for the conversion of temperature values. So, for a 100 degrees Celsius, which is the boiling point of water, the temperature in Kelvin is about 373 using equation 2. Looking closely at the relationship between pressure and temperature, we see that 0 Kelvin or -273 Celsius, the pressure is at minimum or zero. The graph shows the relationship for the absolute pressure versus temperature for constant volume low density gas thermometer. Thermal equilibrium occurs when we have two or more bodies which interact with one another and reach a point where both bodies will have the same temperature. We can observe this when we pour hot water to a cold water, which eventually reaches an equilibrium where the temperature is neither hot nor cold but warm. Here we have the Zeroth law of thermodynamics, which says that, if a system C is initially in thermal equilibrium with both systems A and B, then A and B are also in thermal equilibrium. So, we get that if temperature of system C is equal to both temperatures A and B, then temperature A and B are the same. Metal bridges have these gaps between them that are intentionally placed to counter expansion and contraction of metal, which happens during hot days. When objects are heated, they typically expand like concrete or brick walls, and this phenomenon is called thermal expansion. Increasing the temperature of a material promotes increase in vibration of the atomic particles inside that material. Here we examine linear expansion of materials. As shown in the figure, when a rod is heated to a temperature delta T, it expands to a length of about delta L. When it is further increased to twice the delta T, its change of length also increases to twice delta L. We see that the expansion is proportional to the change in temperature. Shown in equation 3, the equation for the change of length, which is equal to the initial length times the coefficient of linear expansion of the material and times the change in temperature. To account for the behavior of different types of material subjected to heat, the coefficient of linear expansion varies for different types of material. Here we can expand the concept of linear expansion to 2 and 3 dimensions. He waves the volume thermal expansion, where the change in volume is proportional to the change in temperature. The coefficient of volume expansion is simply just a factor of the coefficient of linear expansion times 3. Similarly, for the area thermal expansion, the change in area is equal to the initial area times twice of the linear expansion times the change in temperature. Here we have a list of different materials and their coefficient of linear and volume expansions. We see that the type of material dictates the amount of expansion or contraction during thermal exposure. We see that the larger the coefficient, the larger the change in size. Here we have an example on volume expansion. The volume of a glass in a certain temperature is a 200 centimeter cube. By what percent will its volume increase if the temperature rises by 80 degrees Celsius? The coefficient of linear expansion of the glass is A equal to 4 times 10 to the power of negative 6 over degrees Celsius. We recall the equation for volume expansion and substitute the given values and solve for the change in volume, which is about 0.192 centimeter cube. To get the percent increase, we take the ratio of the change in volume over the initial volume times 100%. We get that when the glass is heated it expands to about 0.096%. Here we look at the strange behavior of water. When the temperature is from a 0 degree to 4 degrees Celsius, the volume of water decreases with increasing temperature. This is strange because we normally expect that when objects are heated the object increases in size. But this behavior only happens between these temperature ranges. For temperatures greater than 4 degrees Celsius, the volume increases with increasing temperature. Here we look at frozen lakes. As the water freezes from 4 to 0 degrees Celsius forming ice, it floats to the top. Ice floats because it has lesser density compared to its liquid form. This ice creates a thick ice layer that acts as an insulator. Since the temperature is low enough that organisms such as fish is able to survive. For the plant life, it is most likely that the layer allows sunlight to pass through, thus it is able to survive also. We recall the expression of density, which is the ratio of mass over the volume. This suggests that density is inversely proportional to the volume. We know that size of the material is temperature dependent, and for hot air balloons the volume increases with increasing temperature. The change in volume reduces its density, which allows it to float in air. Thus we can say that the temperature is inversely proportional to the density. Understanding the concept of thermal stress allows design of buildings to have better resistance against structural deformation. The prevention of contraction or expansion of a material being subjected to temperature change is called thermal stress. The fractional amount of change in length if the rod was free to contract is given as a ratio of the change of length over the initial length. As the temperature becomes lower, both the change in length and temperature are negative. In this figure we have a metal rod that is held by a device that prevents its expansion and shrinkage. The tension force F needed to counter the thermal stress must be equal but opposite with the fractional change of the thermal expansion. For this case, the fractional amount of change in length if the rod was free to contract is given by the rewrite of equation 3. The property that describes the compressiveness of a solid material when force is applied lengthwise is called the Young modulus. The expression for Young is given as the ratio of force over the cross-sectional area over the fractional change of length due to the tension. The fractional change due to the tension that counters the fractional change due to the thermal expansion is given as expression 6. We note that this must be equal but opposite to the expansion for the device to hold the material constant in length. If the length is constant, the sum of the fractional change due to tension force F and thermal expansion must be 0. So, we get an expression 7. We substitute the expressions and rewrite it to get an equation for the tensile strength shown in equation 8. If the temperature is decreased, then the tension F or tensile stress are positive, which means they are pulling the material from shrinking. For an increase in temperature, then the tension F and the tensile stress are negative, which means that they are compressing the material due to its expansion. These are the conditions that may happen when the material is subjected to thermal stress. Quantity of heat and calorimetry. A heat is denoted by the symbol Q, and it is an energy that flows due to temperature differences. Heat travels from higher temperature to lower temperature, which we can observe when we hold something that is cold. We feel that the cold from material is transferring to us, but in reality it is our heat leaving our body. Heat transfer can cause phase change, like when ice turns to water and when heating water turns into vapor. Unit of heat is in calories, or cal for short. 1 calorie is equal to 4.186 joules. You can also have the different units and conversion factors shown here. Quantity of heat is the required physical quantity to raise the temperature of a mass m, and it is found to be approximately proportional to the mass and property of the material. The property of the material refers to the heat capacity that is dependent on the type of material. This property separates what materials are best as heat conductor and heat insulators. The quantity of heat is also proportional to the change in temperature. Equation 9 shows the expression for quantity of heat denoted by symbol Q. Here we have a list of different specific heat capacities of common substances. We see water in liquid form has a very large heat capacity, which shows that the quantity of heat is larger compared to its ice form. Note that the unit has a Kelvin as temperature scale, so take this into consideration when solving problems. Here we have an example. How much heat is needed to raise the temperature of 100 gram water at 20 degrees to its boiling point? Boiling point of water is at 100 degrees Celsius, which we will denote as the final temperature. Using the equation for the quantity of heat and substitute the values. We then convert some of the values to solve the problem, and we get that the quantity of heat needed to raise the temperature is 33,520 joules. Here we have an example. If a lead ball is dropped, its temperature increases when it strikes the ground. Calculate the temperature increase of a lead ball dropped from a height of 20 meters, assume that half of the thermal energy generated on impact goes to the ball. The first position is at a height h, thus it has a potential energy at rest. We assume here that it is initially at rest and falls freely. As it strikes the ground, half of the energy is converted to thermal energy, thus we have at position 2 the quantity of heat divided by 2. Equating the energies at these positions, we have an expression that we can rewrite it to solve for delta T and get that the temperature increase is about 3 Kelvin. Here we have a styrofoam cup containing ice and water. It demonstrates a system where heat is conserved, which means that the styrofoam cup acts as an insulating body that reduces the loss of heat to the environment outside the cup. The cup can be considered as a calorimeter. Calorimetry means measuring heat or the exchange of heat from the quantities inside the calorimeter and including the cup. Initially, the styrofoam cup and water are in thermal equilibrium and the ice is placed later. Here we see that the exchange of heat is among the can, water, and ice. The total heat energy is equal to 0 since the system is conserved. Since ice has the lowest temperature, then we will assume that it will gain heat from the other two quantities. Its sign is expected to be positive to indicate this. The other two quantities, the water and styrofoam can, will lose heat which the ice will gain, and they will both have a negative sign as an indication of loss. Problems involving calorimetry are imagined this way on the interaction among the quantities in a calorimeter system. Here we have an example for calorimetry. In an experiment, A 0.20 kilogram of insulated aluminum can contains 300 grams of water at 25.0 degrees Celsius. The can and the water are in thermal equilibrium. Then a 0.10 kilogram metal block whose temperature is 80 degrees Celsius is placed in the water quickly. It is then covered immediately to avoid heat loss. Using the thermometer, the final temperature of the can, water, and block is at 30 degrees Celsius. Determine the specific heat of the metal block. Here we write the given values based on the problem and its conditions. We draw the problem and see that there are three quantities that interact by exchanging heat. We then write the equation for the conservation of heat energy. These three quantities are the Q from the aluminium can, the Q from the water, and the Q from the metal block which has a higher temperature compared to the can and water. So, we can imagine that this one will lose heat and the other two quantities will gain heat. We then write the equation corresponding to these quantities and rewrite it to solve for the specific heat capacity of the unknown metal. We get that the value of the specific heat capacity is 1439 joules per kilogram Kelvin. Phase refers to the state of matter such as solid, liquid, gas and plasma. When ice melts it is called a phase change. Phase change is a transition from one phase to another. It is also called phase transition. For any given pressure a phase change takes place at a definite temperature, usually accompanied by absorption or emission of heat and a change of volume and density. To convert a 1 g of ice from 0 to 80 degrees Celsius it would require an 80 calorie quantity of heat. Recall the transition of phases. For solid to liquid we call it melting and the reverse is freezing. Solid can be converted directly to gas and gas to solid by deposition and sublimation, respectively. Gas can be converted to liquid and liquid back to gas by the process of condensation and vaporization, respectively. Gas can be converted to plasma and plasma to gas by the process of ionization and deionization, respectively. We note that the enthalpy increases as the order of atoms move towards higher disorder. So as the phase moves from solid to plasma the enthalpy increases. Here we have a graph of temperature versus heat absorbed for 1 gram of water. We start with its solid form of water which is ice and changes its phase to liquid. So, we see that the process of transition requires some time to convert from one phase to the other. We see that it requires more heat at constant temperature 100 degrees Celsius to convert from water to vapor. Before the transformation from ice to water, the ice temperature is first raised from -20 degrees Celsius to 0 degrees Celsius and then melts to liquid. The liquid is then raised from 0 degree to 100 degrees Celsius before it starts to boil and then transforms to gas. The gas is then raised from 100 degrees to 140 degrees Celsius. The quantity of heat that is related to transformation is called the latent heat of fusion and vaporization. Fusion here refers to the process of solidification of liquid and its opposite. Vaporization here refers to the transformation of liquid to gas and vice versa. So if we examine the graph of temperature versus heat, this would be the changes of heat being transformed from solid to gas as shown in the figure. We can write the conservation of energy into the sum of Q ice plus Q fusion plus Q water plus Q gas. The sign convention for the latent heat of fusion is that when it is transforming from ice to liquid due to the melting process, it is positive latent heat of fusion. The opposite when it is freezing from liquid to ice, it is negative. For the latent heat of vaporization, when it is transforming from liquid to vapor, it is positive. The opposite when it is from gas to liquid, it is negative. Here we have a list of values for latent heat for different types of materials. Different materials have different levels of needed to transform from one phase to another, and the latent heat property incorporates this behavior in the equation. Here we have an example on phase transition. A 74.0 gram ice cube of ice at -12 degrees Celsius is placed on a 10.5 kilograms block of copper at 23 degrees Celsius, and the entire system is isolated from its surroundings. After a few minutes, the ice has melted and the temperature of the system has reached equilibrium. Calculate the final temperature of the system. Here we write the conservation of heat, where we have the Q ice melting to water, Q water from ice melted raised to final temperature, and Q copper. We calculate each heat equation. First, for Q ice, which is being raised from the initial temperature of -12 degrees to 0 degrees where the ice will melt. The energy needed to raise the temperature is given as 1776 joules. Letter B is for the melting process. We use the latent heat of fusion process. The energy needed for the melting of 0.075 kg of ice is 24,716 joules. For letter C, we have the water from melted ice being raised to the final temperature from 0 degrees Celsius. So we have an equation as shown here. We also raise the temperature for the copper from 23 degrees Celsius, and it is given as an expression here. We then substitute the values obtained from A to D to the conservation of energy. We rewrite it as an expression solving for the final temperature at equilibrium, which is about 15 degrees Celsius. Here we have an example of phase transition of ice to gas. How much heat is required to convert 12 gram of ice at -10 degrees Celsius to steam at 100 degrees Celsius? We see from the figure that there are 4 heat quantities starting from raising the ice temperature to 0 degrees where ice becomes water. At the process of converting ice to water, it undergoes melting as expressed by the latent heat of fusion. Here the quantity is positive since it is gaining heat. Then we raise the temperature of this converted water to 100 degrees where water becomes gas. Then the process of boiling of water to gas, we have the latent heat of vaporization equation. So, the total energy is given as the sum of these 4 processes as shown in the equation here. So, for the first equation shown on letter A, the mass of ice being raised to melting temperature from -10 degrees to 0 degrees is about 240 joules. Then for melting the ice, it is shown in letter B, where it is positive 40,000 joules. Then for raising the temperature of the converted water from 0 degrees to 100 degrees, it is shown in letter C, and it is 5,028 joules. Then shown in letter D, which shows the mass of ice being vaporized, is positive 27,072 joules. We take the sum of these quantities of heat, which is 36,348 joules. This is the amount of heat energy needed to convert 12 grams of ice at -10 degrees Celsius to gas. Here we have an example. A copper calorimeter can with a mass of 0.1 kg contains 0.15 kg of water and 0.012 kg of ice in thermal equilibrium at atmospheric pressure. If 0.495 kg of lead at a temperature of 200 degrees Celsius is dropped into the calorimeter can, what is the final temperature? Here we assume that no heat is lost to the surroundings. We also listed the given values. Here we have a drawn figure of the problem. We have the ice cube, water, and copper calorimeter that are in equilibrium condition where their initial temperature is 0 degrees Celsius. So the heat for the ice is 0 since it is raised to 0 for its phase transformation as shown in letter A. For ice being melted we have the process for fusion where as shown letter B. The water from converted ice is then raised to the final temperature shown in letter C. The initial water is raised to final temperature as shown in letter D. The copper calorimeter is also raised to final temperature as shown in letter D. The lead block that was initially at 200 degrees Celsius is then lowered to the final temperature as shown in letter F. We then substitute the values obtained to sum of energy. We rearrange the formulation to have an expression for the final temperature. We get that it is about 11.3 degrees Celsius. This is the final temperature of the system after a hot lead is dropped into the copper calorimeter can. Mechanism of heat transfer is essentially the transfer via the difference in temperature of two bodies. Here we have three processes of heat transfer: convection, conduction and radiation. Convection is the transfer via movement of physical mass such as the hot water moving towards the surface of the pan, which creates a transfer of heat. Conduction is the transfer via physical contact of two objects with different temperatures such as this hot pan handle transferring heat to the hand. Radiation is the transfer via electromagnetic radiation where we see here the heat waves transferring heat to the pan. Metals are good conductors due to closeness of the molecules compared to liquid and gas. Liquids are conductive due to the separation distance of the molecules. However, gases are poor conductors since their molecules are farther apart compared to the two phases. Here we have two rods of different temperature in contact. The heat travels from hot to colder temperature as indicated by the green arrow. The equation that describes this is given as equation 13. This is the quantity of heat flowing through a body is given by heat current, H. Here K is the thermal conductivity of the material, A is the cross-sectional area, IT is the temperature difference and D is the distance between 2 points whose temperature difference we are considering. Here we have two rods with different sizes and of different temperatures in contact. The direction of heat flow is the direction of increasing X. A. Since heat flows in the direction of decreasing T, a minus sign is introduced in order to maintain H as a positive quantity. The size of the rod varies with changing distance and this is represented as a temperature gradient as shown in the equation. To incorporate the different properties of a material, we have different values for the thermal conductivities K as shown in the table. This allows us to model the behavior during conduction. Here we have a heat transfer equation for convection and radiation. For convection it is given by equation 15 where HA is the convection coefficient, A is the surface area and delta T is the temperature difference between surface area and body of the fluid. For the radiation, the heat transfer is given by equation 16. For radiation, E is the emissivity, A is the surface area, T is the absolute temperature, sigma A is the universal physical constant called the Stefan-Boltzmann constant. Here we have an example on heat transfer. So, heat is conducted through a uniform copper rod that connects a boiler holding pressurized steam at 200 degrees and a large insulated container of ice water at 0 degrees. The rod's length is 20 centimeters, and its cross-sectional area is 4.00 centimeters. At steady state, find the rate at which heat is transferred. Using equation 13 for conduction, the heat transfer is 154 watts or 154 joules per seconds. Here we have an example. Suppose an electric water heater has a cylindrical tank 60 cm in diameter and 50 cm long. It is then insulated with 3 cm of glass wool. The water tank is at 70 degrees Celsius and the outside of the insulating jacket is at 20 degrees Celsius. At what rate does the tank lose heat to the air around it? Here we draw the problem and note that the wool insulator has a thermal conductivity K equal to 0.04 watts per meter degree Celsius. The equation for heat exchange equation for conduction has an expression that requires us to measure the area of a cylinder. Note that the area of the cylinder is equal to 2 pi RH plus 2 pi r squared. We have the area of a cylinder equal to 0.48 pi m squared. Substituting the values for the thermal conductivities, area, temperature difference, and distance between two temperatures, we get that the heat exchange for the cylinder is about 100 watts or joule per seconds as heat is released to the environment with a colder temperature. That is it for now, and I hope you learned something new today. For questions and comments you may send them to diyeslearningstuff@gmail.com. You may review the slide on YouTube at Dies Learning Stuff. Note, please do not forget to use your school email. Also write your complete name and a class section. Thank you for listening and see you next module.